So I'm just standing here in a small remnant of a pretty decent native plant community and surrounded basically by patches of cheatgrass, knapweed, and leafy spurge. And my main interest is to try to figure out how plant invasion changes these communities, both above ground and primarily below ground. And so the first thing I want to do is try to see, I'm focusing on arbuscular mycorrhizal fungi, which I think are important for these native plants. And I want to see if fungal community composition is different in these native areas and how plant invasion changes that, both in terms of community composition and also fungal abundance. Because fungal diversity, we know, can be important for functional diversity. They're providing a lot of different functions. So it's important to know that if we're trying to reestablish native vegetation. And the only way we can find that information is to go out and see what's actually colonizing native vegetation. But I'm going to try not to limit myself to arbuscular mycorrhizal fungi. I also want to look more into how does plant invasion change ecosystem processes, such as soil respiration, decomposition, and also nutrient cycles. For example, cheatgrass is an annual grass, and it dies in May or by the latest June, and then start to decompose, and that can have huge influences on not only nutrient dynamics but also respiration. So I'm going to try to focus on this and measure that on 3 different areas on the property. And we've just, with Dan's help, we just found one good site that has pretty pure stands of natives, and we'll go to the other invaded areas after this. But I just want to demonstrate how I'm planning on doing this. So one way we can measure soil respiration, and the way I'm planning on doing it, is to bury these tubes, putting this into the ground level, filling it up with soil again. And obviously that will be a huge disturbance, but over time I think that will sort of even out. And what I'm hoping to do is have 3 different mesh here. One that allows roots to come in, and a much finer mesh that only allows hyphae to come in, and the finest mesh that excludes both roots and hyphae, so we only measure essentially bacterial respiration, like the basal respiration. And this will tell us not only how, and I'm gonna bury these in native areas and invaded areas, and that will tell us not only how respiration may differ between native areas and exotic areas, invaded areas, but also how important roots and fungi are for overall respiration of CO2 emissions. And that's of course also interesting in the whole global change scenario, because we want to try to figure out how does all these changes that are occurring in plant communities contributing to changes in CO2 emissions. Nutrient dynamics I'm going to follow by this little thing. It's resin capsules, and they're small little spears in this pantyhose that are able to absorb nutrients that are available to the plant roots. So it's essentially an infinite sink of nutrients, and we bury that in the soil for a certain amount of time, and then we can go and find them again and actually extract the amount of nutrients that are bound to these, which will give us an idea. And if we do that over time, we can get an idea of temporal nutrient dynamics. For example, when cheatgrass dies, is that associated with a nutrient flush? And I'm also planning on burying these litter bags that contain dead shoot biomass, and we're also playing with the idea of using roots, bury them in the soil to look at decomposition and how plant invasion changes microbial communities and decomposer communities. And here I'm interested in the rate of decomposition, and also to see if native decomposer communities are better at decomposing native plant material compared to invaded plant material. So if that whole process changed with invasion. So this is just a leafy spurge invaded area, and almost, I mean, it's close to monoculture, and it just begs the question, like, how are processes, below ground processes, different here from the native area we were just in? And that's what we're going to try to figure out. There's a little bit of cheatgrass in here for sure, but it's just dominated by leafy spurge. Because cheatgrass grows so early in the spring, they're basically done when the leafy spurge is coming on, so they're occupying completely different niches. Whereas, you know, leafy spurge with native grasses, you can imagine them having a more direct competition.
Deep roots.
Yeah, yeah, exactly. Roots. That's a good point. You know, cheatgrass, very shallow root system. Leafy spurge can go down literally meters into the soil. Different ways of dispersing. I mean, it probably comes in as seeds, but then it's just spreading by roots, rhizomes going out, which makes them so successful because they're clonal. So they can be in one spot, and it's a sunny spot, and they can allocate carbon to another part that is in a shaded area, where there might be a lot of nutrients, for example. So you have this exchange within this organism that can make it a very successful invader. So we're just pulling up some roots here of leafy spurge, and you see this white resin that comes out. It's actually toxic to some people. It can cause blisters. I hope it doesn't do that for me. Sheep loves this for some reason. It's hard to imagine that they can actually tolerate this. And also you can imagine fungi coming and colonizing these fine roots. How are they affected by this white resin? We don't really know, but it could potentially be a strong selection pressure, that there are certain fungal species that tolerates it, but others that don't like it. So I wouldn't be surprised if this is one that we can find very different fungal communities in leafy spurge just for that reason. See, they're already starting to grow. So this finally is our knapweed patch. Knapweed is interesting because there's been a few greenhouse studies that seem to indicate a mycorrhizal role in their interaction with natives. So when they've inoculated plants, so they grow with the fungus, when knapweed grows with native, it actually grows a lot bigger than when it grows only by itself. And I think so one hypothesis has been that they're stealing carbon from their neighbor via the mycorrhizal fungi, which is probably very unlikely. But more likely could be that they could potentially have a subsidized symbiosis. So because the interesting thing with mycorrhizal fungi is that they're not host specific. So you could have the same fungal individual colonizing a knapweed and also colonizing this cheatgrass, so colonizing a native. And the plants give carbon to the fungus and in return gets nutrients such as phosphorus. And we don't really know how this exchange happens. So it's possible that knapweed may pay less for the nutrients that they get, so they kind of get a subsidized symbiosis. And that is one way maybe they become so competitive. But first of all, we need to figure out also who are colonizing these knapweeds. Are they the same fungi that are also colonizing knapweed, or the natives? Because if they're totally different, it's not likely that they actually share the same, well, they're in the same mycorrhizal network. So that's the first thing, just to see who's here.